Okay, so in this video, we are going to learn how to integrate when we don't have exactly x to the nth. So let's talk about where we've been. So what we have so far going on is if we have x to the third plus x squared dx, I can easily find the antiderivative by increasing the power by 1 and dividing by the new power. But what if I had a situation that was like the indefinite integral of 2x plus 1, close it to the 5th power dx? The only way I can integrate that with what I know to create x to the nth is I'd have to multiply that binomial out, 2x plus 1. I'd have to multiply that by itself 5 times. I'd have to expand it and multiply it by 5 times, and that would be, quite a long process. So there's an easier way of doing this called U-substitution, and essentially it's about 3 steps. The first step is to identify what will be your U. The U will be the inside stuff of the quantity. So U is going to be equal to 2x plus 1. The second step is I'm going to take the derivative of U with respect to x. So the derivative of U is du. The derivative of 2x plus 1 is 2 dx. So simply put, so far, you choose U to be the inside of your quantity. You take the derivative of U with respect to x in the second step. And now the third step is where it gets a little tricky. We are actually going to return back to the integrand and convert all of that in terms of U. So I know already that this will become U to the 5th. But I still have that dx hanging out here, and I can't integrate this until that dx becomes a du. But notice in this second step, du equals 2 dx. So what I can do is I'll put a constant of 2 in. We know in math, we just can't put in something, without compensating for that. So I'll put in a factor of 2, but to compensate for putting in that factor of 2, I'll take out a 1/2 so that it's equivalent to 1. And what happens is that 2 dx now becomes my du with a 1/2 in front. And now I have something I can integrate. It's no longer x to the nth, but it's u to the nth. And that antiderivative would be 1/2 times u to the 6th over 6 plus c. And you must restore it back in terms of the original variable, which is x. So that would be 1/12 times 2x plus 1 to the 6th plus c. And as always, as a check, you can take the derivative of that, dropping down the power, multiplying it by what's in front, repeating the inside, decreasing the power by 1, and multiply by the derivative of the inside. I think we all agree that 6/12 is a 1/2, and a 1/2 times 2 is 1. And notice I end back up with what I had originally in the integrand. Okay, so let's do some more practice. The indefinite integral of x times 3x squared plus 2, close it, cube it, dx. First step, choose a u. So I'm going to choose u to be the inside stuff, which is 3x squared plus 2. My second step is the derivative of u. So that's du equals 6x dx. Make sure you attach the dx. Otherwise, you're not going to be sure or clear on how to build up your integrand. In the third step is when you go back to the original integral, and everything has to now be in terms of u. So I'm going to make this u to the third, because that's what I had let u be equal to. But everything else surrounding that u to the third has to become a du. So notice that my derivative of the inside was 6x dx. The integrand has an x dx. So I'm going to put in a factor of 6, but I will take out its reciprocal to compensate for that. So it's equivalent to 1. Then this will now become my du. And now I will have 1 over 6 in front times the indefinite integral of u to the third du. And then now I have created that form I know of, u to the n. So it's 1 over 6 times u to the fourth over 4 plus c, which is 1 over 24 times 3x squared plus 2 to the fourth plus c. Okay. Another one. The indefinite integral of the square root of 3x plus 2 dx. First step, choose my u. I'm going to choose the u to be the inside stuff. Second step, take the derivative of that with respect to x, which is 3 dx. The third step is when I return back to the integrand and convert everything in terms of u. So I obviously know that this will become my u, but that dx is still hanging out there in the integrand, and that has to become a du for this to work. So I'm going to put in a factor of 3. So then now that becomes a 3 dx. But to compensate for putting in that factor of 3, I'll take out its reciprocal, which is 1/3. And now that 3 dx will become a du. And now I hopefully have something I can integrate. Well, that square root of u is really u to the 1/2 du, which is the same as u to the nth. When I increase it by 1, that 1/2 that is, I'll get u to the 3/2 times 2/3 plus c. Don't forget to take the reciprocal of the 3/2, which is 2/3. So it's 2/9 parentheses 3x plus 2 to the 3/2 plus c. Step 3 is usually the trickiest step, is when you return back to the integrand to convert everything in terms of u. Okay, another problem. The indefinite integral of 2x dx over parentheses 3x squared minus 1 to the third power. Okay, think to yourself, what will you choose as your u? I think we agree. I hope that our u would be the inside stuff, 3x squared minus 1. The derivative of that is 6x again, dx. Don't forget the dx. In step 3, I'll return back to the integrand. I've got a 2x dx, but I need that to become a 6x dx so I can replace this with the du. So what I'll do is I'll just take out that constant of 2, and I'm going to put in a 6, but I'll always take out its reciprocal, which is 1/6. Now the 6x dx becomes the du, and this becomes u to the third in the denominator. So obviously 2 times 1/6 is 1/3 times du now over u cubed. But remember, that's still not u to the nth. So I've got to create that by rewriting that as 1/3 indefinite integral of u to the negative 3 du. When I increase it by 1, I'll get u to the negative second, divide by negative 2, times it by 1/3 yet, plus c. And that will become negative 1/6 of 3x squared minus 1 to the negative second plus c. And you can also kick that down to the denominator, but it's good. Okay, indefinite integral of e to the x times 2e to the x plus 4 to the 5th power dx. Okay, go ahead, choose your u. U would be equal to the inside stuff. It's really the chain rule backwards. The derivative of u with respect to x is du equals, well, 2e to the x, and that derivative is 0. Okay, in step 3, we're going to return back to the integrand. I'm going to make this a u. So what do I have so far is u to the 5th and this other stuff all in terms of x, and that won't work. So my derivative right here, du, is 2e to the x dx. I've got e to the x dx right there. I've got this part. But I need that 2. So I'll put in the factor of 2 anywhere you want, doesn't matter as long as it's in the integrand. But to compensate for putting in that factor of 2, I'll take out its reciprocal, which is 1/2. So this cleans up to be 1/2 the indefinite integral of these two here multiplied give me the du, which is right here. And that is u to the 5th. And then that would be 1/2 times u to the 6th over 6 plus c, which is 1/12 times 2e to the x plus 4 plus c. Okay, another one. Indefinite integral of the cosine of x times 2 plus the sine of x to the 1/2 power dx. All right, what will we choose as our u? I think we're pretty clear that we'll choose u to be the inside stuff. We'll take the derivative of u. Remember, the derivative of sine is cosine. And in step 3, we're going to return back to the beginning. I seem to have a perfect match. This here will become my u. I seem to have a cosine x dx, which is du. All of that becomes my du. So I don't have to worry about the derivative of the inside was present in the integrand. The derivative of the inside was exactly in the integrand as it appears. The derivative of the inside, which is cosine of x dx, appears exactly in the integrand. So I don't have to put anything in and take anything out. So it becomes the indefinite integral of u to the 1/2 du. Increase that by 1, get 3/2 times 2/3 plus c. But I'll put everything back in terms of the original variable, x. And there's my function. Okay. And one more. The indefinite integral of 1 plus ln of x to the 2nd all over x dx. All right, so I'm going to choose the u to be the inside, which is 1 plus ln of x. The derivative is, well, the derivative of 1 is 0. The derivative of ln of x is 1 over the inside times the derivative of the inside, which is just 1. And in step 3, I will return back to the beginning. This will become the u. Now that x, that derivative of the ln of x, which is 1 over x dx, this x better be in the denominator. And by the way, dx is never in the denominator. dx is never in the denominator. So 1 over x dx appears exactly. So it's just going to become my du. This is the indefinite integral of u squared du. which would be u cubed over 3 plus c, which would be 1 plus the ln of x cubed all over 3 plus c. All right, and just one more. The indefinite integral of, let's change that to our normal color here for red so it stands out. The indefinite integral of, say, secant squared of 2x over the square root of tangent 2x dx. Well, this time we've got two inside stuff. We've got the secant in terms of secant, we got the square with the secant being on the inside, and we've got the square root with the tangent being on the inside. But remember, we always want to choose a u so that the derivative is in the integrand. The derivative of u has to be in the integrand. So I'm going to try to choose u to be tangent 2x because its derivative, secant squared, is in the integrand. So the derivative of tangent is secant squared, repeat the inside, times it by the derivative of the inside. So now in step 3, I'll return back. I'll cross this out, make it a u, because that's my u right here. And all this has to become the du. Well, it matches this, provided I put a 2 in and take out a 1/2. And this becomes 1/2. And all that on top becomes my du, because du is secant squared 2x times 2 over the square root of u. But again, that's not u to the nth. So I need to rewrite it as u to the negative 1/2 du. And when I increase it by 1, by adding 2 over 2, I'll get u to the 1/2 multiplied by its reciprocal. And then now I'll get the square root of tangent of 2x plus c. And there you have integration by U substitution.